welcome back for Lecture 13, Part 1, where in this part, we're going to discuss different forms of energy so that we better understand the different components of our energy balances. And you may see that a couple of the terms are very similar to things you're familiar with from your physics and chemistry classes. So to start off, we've got one of the oldies but goodies, external kinetic energy, where, as you may remember, kinetic energy is equal to 1/2 mass times velocity squared, where your units are going to be kilograms times meter per second squared, which turns into newtons times meters, which ultimately will turn into our unit of energy, joules. And as you may remember, when you have no change in velocity, that means that you have no change in kinetic energy. All right, pretty simple so far. Good. So the next type of energy we have, as you probably have guessed at this point, is our external potential energy, where potential energy is equal to your mass times gravity times height. And in this case, if you have no change in height, you have no change in potential energy. Okay, solid. So now we've got two forms of energy that we're pretty familiar with. This next one, it's a little bit different, and that's why I'm going to use a block to help me explain that third one. So with our block, as we've just discussed, that block can have a certain amount of kinetic energy. If I throw the block, it can have a certain amount of potential energy if I place the block at a very high location. But there's also an energy associated with the block being the block. And that's called internal energy. It's all the energy necessary to make the block into the structure it is. So it accounts for the vibrational energy, the rotational energy of all your atoms and molecules within your block, and the energy associated with getting these atoms and molecules in the positions that they're located in. And so it just covers everything necessary to create your system, which is a cool idea, but it also makes things a little bit challenging, because when you're dealing with this internal energy, there's no way to measure where zero is. Yeah, there's no clear-cut place where you can say, oh, yes, that is zero internal energy. And because of that, we actually are going to have to define a particular state and say, okay, this state is going to be our zero reference state, and we're going to look at changes from that state. So for us, our workaround for not knowing what true zero internal energy is that we focus on changes in internal energy. That's the only thing that will matter to us. And our internal energy is mainly a function of temperature. So there are some scenarios that we can look at and say, oh, well, in this case, because changes in temperature are minimal, we can say that we have no change in internal energy. So, for example, if you have a constant temperature, you're isothermal, you have a small change in pressure, so it's less than a few atm, and there's no phase change or chemical reaction, then the change in your kinetic energy is going to equal zero. And if you have, let's say, an ideal gas, you'll have a change in internal energy of zero when you have a change with pressure at a constant temperature. Similarly, for liquids and solids, you can assume that the change in internal energy is about zero when you have a change in pressure at a constant temperature. All right. Okay, and so now moving on to our next form of energy, we have heat. And for us, that's the energy transferred to our system from the surroundings. However, if you have a system that is insulated, or you have the temperature of your system is equal to the temperature of your surroundings, then you have no heat being transferred. And you can say that Q equals zero. And if you ever see the term that the system is adiabatic, that is an indication that your Q term is going to be zero. That indicates that no heat is being transferred throughout the system. And our final form of energy is work, which is something I think you're familiar with, and it's the force applied over a distance. And so for us, there's also some times in which we can assume that our work is going to be zero. So if there are ever no moving mechanical parts, so we have no piston, no mixer, pump, or turbine, there's no electrical current or other non-temperature driving forces crossing the system boundary, then we have our work being equal to zero. And most of the time for all the problems we're going to be working on, the real thing you just want to focus on is finding the words no moving parts. And if you see no moving parts, that's your cue to assume that we have 0 work. And for heat and work, there's a sign convention that we should be aware of with regards to in which situations is heat and work going to be positive and which are we going to have something negative. So what I've got is a box to represent our system. And in thermodynamics, there's different, depending on who you speak with, different folks define they say that going in is positive or energy coming out is positive. It kind of depends on who you deal with. For us, what I wanted to make sure is that we're on the same page, and we're going to say that any energy entering our system is going to be positive and energy leaving our system is negative. So in this case, for your Q and W and your heat and work, if you have energy coming in, it's positive. If you have energy coming out, it's negative. Okay, so just remember, anything coming into our system for heat or work is going to be positive. It's something added into our energy balance. And if we're having heat or work being dispensed by our system, then we are losing energy from our system. We have a negative amount of energy. Or we'll say that it's a negative amount. Okay? And so that wraps up part 1 of lecture 13, where we just discussed the forms of energy. And now moving on to part 2, what we're going to do is we're going to set up energy balances for closed and open systems. So I hope you're excited, and I'll see you for part 2.